Okay, so let's get started. Okay, so I mean, Mishkat has been around so many times, but I think it's always a pleasure kind of introducing him. So Mishkat did his BTech in engineering physics from IIT Bombay, PhD in physics from University of Rochester, and that's where I know him from. And after that, he did several postdocs, Georgia Institute of Technology, University of Arizona, University of Maryland, College Park, and then he joined RIT in 2011 as a faculty. So Mishkat and his group is broadly interested in light matter interaction from the perspective of fundamental science as well as technological applications. And currently he's focusing on the interplay of electromagnetic modes of radiation such as laser light with the nanofabricated components such as mechanical oscillators and rotors. So today he is talking about theory of optical rotation of a few ion crystal. So since this is a quick talk, I mean, quantum information and coherence talk, this is supposed to be very informal and kind of tutorial type. So anybody who has questions, just feel free to kind of, interrupt and ask question even in the middle. So with that, I will let Mishkat start. Over to you, Mishkat.
Thank you very much. Thank you. Thanks for the introduction. And always thanks to Anand and Saikat and Harsha for organizing this. And it's a substitute for my annual pilgrimage to IIT Kanpur, which I really enjoy, and for both academic and non-academic reasons. But hopefully everybody is fine and safe. And it's nice to see so many students also join. Unfortunately, I cannot see the full panel. Okay, I can see myself now. And then, okay. So I will talk about optical rotation of few ion crystals. And I took the word theory out of the title because actually now we have some experimental data, and I will describe in detail. So you can see some of the data up here. And everybody see these images?
Yes, yes.
Okay. So I'll describe these in a little more detail. So first I want to say that I am actually presenting the work of my postdoc, Arpita, who is here with us. Arpita, can you show your face for a second and say hello to everybody?
Hi.
That's Dr. Arpita Pal. She came to my group from Dr. Bimalendu Dev's group at Cultivation in Jadavpur. And she's done an outstanding job of coming up with this theory, basically developed from the ground up, because this is a new direction for our group. I'm an ion idiot. I didn't know anything about ions, and actually probably don't even know even now. But she has developed the whole code, and you'll see that she has generated a theory which has excellent agreement with experiment. So she handled the numerical part of the work. I also am presenting the work of my undergraduate student, Duke. Duke, are you in here? Can you pop up and say hi? Here's Duke.
Hello, everyone.
Yeah, so Duke is really not a physicist. He shouldn't be allowed in here. He's an electrical engineering major. But since you guys are running an engineering institute, I thought we'll let him into the presentation. Duke has done an outstanding job with analytical expressions from the theory, which I personally thought was just too complicated to do anything with, but he has really done a fantastic job. And the analytical part has given a lot of insight and also provided good pieces in configuration space for the numerics to start. One of the tricks with, as I understand it from Arpita's comments, with the numerics is that you have to find the right parameters in configuration space, and this can be non-trivial search if the number of ions is 10, 15, 20, which they've actually gone up to. And Duke's conditions and analysis have really helped. So these are the two people who have done all the hard work. I get to present it, unfortunately, because I had the good luck of hiring them. So this is RIT in what I like to call the high temperature regime. This is in the summer. Please come by if you're visiting anytime. So this is actually a collaboration. So we've done the theory, and then the experimental data you're seeing comes from the lab of Akira Ozawa and then Thomas Udem, who are at the Max Planck Institute for Quantum Optics. So this actually spontaneously happened after I gave a talk there, and Akira very generously took me to his lab. You can see him in his lab here, and showed me some quote unquote funny effects they were seeing. And of course, that's where things typically start. So we started looking at this, and now we're quite heavily into it. Okay. So again, please stop me and ask questions if you have any. So we are going to talk about trapped ions, and these are atoms missing one electron, and they are charged particles. And there is a theorem called Earnshaw's theorem, which places constraints, quite severe constraints, on the trapping of charged particles. So I tried to summarize it in one statement here. This is taught in undergraduate physics. I know Griffiths has a section on it. No collection of charges, electric charges, can exist in stable equilibrium in static electric or magnetic fields. And I'm going to give a hand-waving physics type justification of this theorem. Imagine that there is a particle in stable equilibrium in 3 dimensions. Typically, it would find itself near the minimum of a 3-dimensional harmonic well, because every potential can be expanded to first order in quadratic, every reasonable potential in the coordinates. And typically it would look like this. And I've arranged for 3 different spring constants, kx, ky, and kz, to indicate that the stiffness of the trap along all 3 directions may not be the same. But now, if this potential is due to electric or magnetic fields, which are static, then Laplace's equation has to be obeyed, which means del square u has to be 0. And you can take the derivatives and convince yourself that this means the sum of the 3 spring constants has to equal 0, which means at least one of them has to be negative. And that means you cannot have stable confinement in all 3 directions simultaneously, more like a saddle point where if we sort of imagine that gravity is acting along the z direction, there is confinement along z, and you can see from the shape of the potential that there is confinement along x, but if you push the particle along y, it will just roll over, okay? And so it's unstable in that direction. At least one direction of motion is unbounded. And so it's impossible to trap a charged particle. Earnshaw wrote his theorem at a time when only classical physics was known, but his results often carry over to quantum physics and ions quite robustly. And this is true also for trying to trap ions with electric and magnetic fields. So intuitively, one feels maybe using time-dependent fields, you could violate Earnshaw's theorem, and this is true. And if we use this figure for intuition, we can convince ourselves that maybe if we spin this saddle around the z-axis fast enough, then some particle at the center of that minimum here along x, which is now spinning, will be restrained by the saddle before it rolls off along any particular direction. Okay, so this is where I have to break off and present my little animation, hopefully. So you see, it's possible, basically, if the saddle rotates faster than the ball oscillates, to confine it quite stably, actually. Now you see it's almost occupying just one point. Another thing to note is that on top of the harmonic motion, there is this precession of the ball going on. So I'll have something to say about that in a second. Okay. So what happens? So you can actually confine an ion like that by rotating the potential in that way. More commonly, what happens is that you switch between having confinement along X and then along Y. So if you plot the potential, it will look confining like that, become flat, and then go up along the orthogonal direction. Okay, so you just switch between these two configurations, and you'll get pretty decent confinement. And if you follow the coordinate of the ion along either of these two directions, you will see the harmonic oscillations, which are the big amplitude oscillations here. But on top of that, you'll see this micromotion, okay, which is basically the precession or jiggling of the ion. And here's a schematic of how this is done with electrodes and fields, and sort of a conceptual way of showing the switching of the confinement between the two perpendicular directions. Okay. One thing to remember.
So Mishkat, sorry, the micromotion is because of the rotation, right? The rate at which the potential
Yes.
is being, yeah, okay.
What I want to point out is that the micromotion exists everywhere. Yes, Harsha, that's right. It's basically due to the saddle oscillating. And you are free from it if you are at the very center of the coordinate system. Okay, so that point is where people try to trap. If they're trying to trap a single ion, they try to trap very near the center and minimize the effects of micromotion. You can stretch the trap out. So here we have now these 4 electrodes and these end caps, and you can stretch it out so that you can put more than one ion in there. And as long as they're close to this axial line, they don't see much micromotion. If they're off of that axis, then they will see micromotion. So these ions their motion can be cooled using optical beams, and if their temperature is cold enough, then their mutual Coulomb repulsion and the confining trap will equilibrate at some point, and they will line up nicely into what's called a Wigner crystal. Okay, so this is sort of the this is what's called the linear Paul trap. This is named after Wolfgang Paul, and this is sort of the workhorse of quantum ion trap-based quantum computation, because now you have an array of atoms, each one of which can be used as a qubit. They also interact with each other, so you can transfer information from one to the other. You can make gates by making 2 or more of them interact at the same time. This thing serves as a bus, so you can shuttle information up and down and so on and so forth. And this usually works inside vacuum and so on and so forth. But the Paul trap is quite robust, actually. So you can trap even more macroscopic charged particles. So here you see grains of flour. And this works even in the open air. Actually, I just saw one in Rajibul's lab at Waterloo, where he actually had these grains. And then you just shine a laser on them and you can see them hanging. And you can actually put a lot of them in there, and they have all sorts of interesting geometries, some of which we will explore. Okay, so in these arrays, the ions are not exactly still. They are oscillating about their equilibrium position. They're vibrating harmonically in a linear fashion. And in fact, there is an enormous literature on the vibrations of such ions and the characterization of those crystals and so on and so forth. You can make all kinds of geometries with the Paul trap. Ion trapping has been recognized with, I believe, 1/2 of a Nobel Prize that went to Wineland. I think Harosh got the other half. And then right now, Wineland's student set up a company which, with venture capital, which promises to introduce the first commercial trapped ion quantum computer, which is, I suppose, competing with the superconducting qubit model. One thing I want to point out is that if you increase the voltage on the end caps, you sort of push this array in, and you can crumple it up. And so you see this linear to zigzag transition, for example. And this will be kind of important to us. And this is Chris Monroe, who was Dave Weinman's student, and Jung Sang Kim. I think both are at Duke now. I think Chris moved from Maryland. Okay, so all this is about linear vibration. Our interest is in actually the rotation of ions. And there's a good bit of interest now because there's a whole bunch of things you can do with ions that are rotating around in a circle like shown here. Okay, so you can do various kinds of rotational interferometry. You can simulate diatomic and polyatomic molecules, because these are essentially molecules, except the bond length is in microns instead of nanometers or angstroms. You can look at the microscopic quantization, test the microscopic quantization of angular momentum. You can have two of them and then make them switch places and test quantum statistics. You can put the ions in a ring lattice and move them around past that lattice to study nanofriction now with periodic conditions earlier on. And Sekar probably knows this. Vuletich did a lot of experiments with ions in linear optical potential. So you just have these ion chains sliding past. And I'll have to say, I have a little bit to say about that later. So that's an interesting area of physics that can be explored using the system. Aharonov-Bohm type experiments, you have this ring, you can send a magnetic field through it, look at the phases and so on, time crystals. Detection of Hawking radiation in analog gravity, I'll have a bit to say about that. And more generally, the rotor presents a sort of different system compared to the linear vibrations, because the energy spectrum scales non-linearly with the quantum number, right? For angular momentum L, because it's L times L plus 1, and it just goes with the excitation number N for linear vibration. So generally, you expect more complex possibilities for Hamiltonian engineering and quantum computation. This is just starting to be explored. So in the past, there has been some attempt experimentally at producing such ions on rings. One of the early ones, 20 years ago almost, was in Munich. These were actually high energy physics guys. They were accelerator physics guys who had a beam of ions, and then somehow they cooled it down enough so that the ions crystallized. So you had basically a crystal rotating, but still it was at fairly high energies. I think it was few Kelvin. There was an attempt in Sandia to have laser-cooled ions assembling in a ring-shaped crystal. And you see the trap here, it's fairly complicated. And they ran into problems with having a homogeneous sort of translational invariant ring, because there was gap for the ion input and so on and so forth. So they saw some things, but weren't very successful. The basic idea was basically to twist what we saw earlier, the linear Paul trap, into circular geometry. And they didn't really follow up too much beyond that. Now, more recently, Hartmut Haffner's group at Berkeley has done some pioneering work. They have this planar trap, which is of the right symmetry. And I believe red is RF and black is ground. So in some sense, this is also a Paul trap, just a circular Paul trap. But they're able to trap ions some distance away, far enough away from the electrodes so that the fields are reasonably homogeneous. And you can see there are two papers. The first one showed that you can, by tuning a biased electric field, basically delocalize about, I don't know, this was 1, 2, 3, 4. I think this one was about 15 ions. I think they went up to 100 maybe around in a ring. Maybe Abhita can correct me if she remembers. And so this, they claim, is homogeneous to a few nanokelvin. Their control over the geometry is so good. So this is a paper I'm going to talk about on my next slide quite a bit. We had already started the collaboration with Munich, and we were into it about a year when this paper came out, and both Akira and I read it on the same day, and our emails crossed because it's a really nice paper and sort of points out the possibilities there are some possibilities in a very, very nice way. So I'll talk about that. So there's a lot on this slide. I apologize for that, but I think, I hope I can organize it for you. So this is the trap seen from on top. These are the two ions, and you have voltages which allow you to rotate a 2-ion crystal. Okay, these are calcium ions, and so not quite the number of ions or the diameter here, but for purposes of illustration, very good. So they claim they have established coherent control over this rotor. So how does that work? If you do not rotate the crystal, the finite temperature will excite a number of propagating and counter-propagating modes, which can be spectroscopically seen by looking at the frequency content of fluorescence from the ions. Okay, so that's what is shown here. These lines are actually the transition lines for various angular momentum changes. So the central one is basically the zero change line, and there is 1 h bar and 2 h bar transition. So this one is from 0 rotation to h bar of rotation. This is from 1 to 2 and so on and so forth. And there's counter rotating pieces here. But what you see is that all the various delta L's are bunched in together. Some of them are overlapping. Some of them are very close to overlapping. So in their experiment, they did not have a laser which could reliably detect these gaps or resolve these lines. So they went to a regime which I thought was pretty interesting. So they actually spun this 2-ion crystal up to a fairly macroscopic angular momentum. Okay, so that was about 7,850 h bar. Now that allows them to separate out the various delta L clumps. Okay, so in the lower picture, you see the 0 to 0, 1 to 1, 2 to 2 over here. And then completely separate is the delta L equal to 1. Okay, so that means going from 7850 to 7851 and so on and so forth. And then the delta L equal to 2, the blue lines are now shifted over to the right. So how does that work? If you work out the energies of this rotor, it's basically quadratic in the angular momentum quantum number, because this piece is very small. It's a small correction, which is non-negligible, but I'm just trying to use this expression now to basically tell you why there are 3 clumps. Okay, so this constant is the intrinsic rotation parameter of the 2-ion crystal in terms of its the mass of each ion, and R0 is the radius of the crystal, which is about 3 microns. Okay, so if you look at the transition energy between two consecutive states which are separated by delta L, and use this first term, you will get 2 terms. Okay, the L square piece will cancel out, and then you have the delta L square piece and the L delta L piece with the 2 in front. Now, if your center of mass orbital angular momentum is very large, the first term will dominate, because L delta L will be much larger than delta L square, up to factors of 2. Okay, and now this means that if the ion crystal is rotating at a fixed frequency, it has a fixed center of mass angular momentum. So all this stuff is constant in front. 2h bar omega r L is constant. Let's pick delta L equal to 0. That's this line. Then let's pick delta L equal to 1. That's the center of this clump, which is quite far away. And then delta L equal to 2 will bring you to the center here. And the other lines you see is because of this term, which we neglected because we were just interested in the center. Okay. So now these lines are sufficiently well resolved for the experimentalists to observe, and you see the spectrum here. And by shining a laser perpendicular to the 2-ion crystal, they are able to couple these discrete angular momentum states, basically separated by a certain delta L. So the coupling matrix element is shown here. laser is assumed to be providing a plane wave. And then we ask what is the coupling between the angular momentum state L and the angular momentum state L plus delta L. And it's not a delta function, it's a Bessel function. So there is a range of couplings. Interestingly, it doesn't depend on L. It just depends on delta L, okay? And this is a distinction between, for example, if these were harmonic oscillator states with n and n plus delta n, the matrix element would actually depend on n, but here it doesn't depend on the quantum number L, just the difference of the two quantum numbers, okay? So this basically means that when you couple these two using a laser, the Rabi frequency at which that superposition oscillates is independent of L. And they were able to observe this Rabi frequency here for two different laser intensities. If you use low laser intensity, then you get a slow Rabi oscillation. If you use a higher one, you get more energetic, higher frequency of Rabi oscillation, okay? And then I'm not going to go into the details because I don't really understand them. They also were able to do Ramsey spectroscopy using the right pulses, pi by 2 and then evolution and then minus pi by 2 back again. So this is Ramsey spectroscopy of the delta L equal to 1 superposition. And then this is the Rabi frequency of the delta L equals 4 superposition. So what do I mean by that? This is the oscillations shown by 7850, a superposition of 7850 and 7851, I believe, because it's delta L is plus 1. And then these are the oscillations shown by superposition of 7850, 7851, 7852, and 7853, okay? They were able to basically select by changing the argument of this. This case of X is actually the angle, involves the angle between the laser and the plane of the 2-ion crystal. And so by changing that, they're able to basically make sure that the coupling is large for only 2 states here and for 4 states. But the 4 states you see dephases rather quickly. Okay. So I'm still trying to come to terms with this experiment because it is not really an experiment done near the rotor quantum ground state. Okay, we're not looking at superpositions of 0 and 1 or 0, 1, 2, 3. Okay, the way I like to think about this, and maybe Saikat, you have something to say, is this is more like a Rydberg atom. You excite to a very large quantum number, which in this case happens to be 7850 h bar, and then you demonstrate coherent transitions around that energy level. So it's sort of there's quantum coherence here, but it's far from ground state. I don't know what that means. I'm still trying to figure it out.
Mishkat, this yes. This Rabi frequency is now the strength of the Rabi frequency is the angle the plane wave makes, right, with the alignment. It is not the strength. Because
the angle is in here. The kx
correct. So
theta.
So it is nothing to do with the intensity, right? I mean, the dominant quantity is the Bessel function.
This is the argument of the Bessel function.
Correct. So Bessel function denotes the strength of the coupling, right? The Rabi frequency. Is that correct?
Yes, but where you evaluate it depends
on that k dot r. Correct.
Yes.
Yeah. So what I'm saying is, it's not intensity dependent. It is angle dependent.
Oh, of the laser, you mean?
Of the laser, yes.
I would tend to agree with you, but I have to check because I'm not sure. So this is not the full matrix element. This is sort of the selection overlap.
Okay.
The Frank-Condon factor, because the laser is not just a plane wave; it has an amplitude in front also.
Yeah. The laser intensity will be there when you.
Will be there. So this is just the Frank-Condon overlap between the two states.
Yeah.
Okay. Right. So if you have some amplitude, it will multiply this plane wave, right? So I think some. But I have to read the paper to see.
Yeah, but
exactly
it's just that factor times the electric field over h bar, no? So
So yeah, there you go. Yeah,
Mm.
something like that.
Mm. Yeah. No, but your analogy with the Rydberg atoms is indeed probably perfect.
You think so?
Yeah, I think so. Yeah, it would make sense.
Because I couldn't understand it. So,
So,
I'm
Mishkat,
still. Yeah, go on.
yeah, so what are the lifetime of the states? Because it seems like it's oscillating for a very long time, like
So
almost a
one is the ground
millisecond.
state. One is the ground state, which is very stable. The other one is a metastable state.
Okay.
Exactly how long it is, I have to go back and check. But it's not. It's metastable states. I don't know. You have a better feeling for this probably. They're microseconds, right? More than they can be.
Yeah, but these are basically the oscillations are lifetimes corresponding to the rotational states, no?
Yes.
And they're very long-lived, it seems.
So here, at least the Rabi frequency is going on for, I don't know, millisecond easily.
Yeah, milliseconds. Yeah, it's amazing.
Yeah, it could even be 10 milliseconds. I have to go back to the paper and see exactly. Yeah. So yeah, that's right. So I guess in that sense, it's a nice result, right? And the coherence is.
But do they show that it's actually due to the two ions versus it's a collective? The L is the collective angular momentum as opposed to single ion transitions.
Yeah. So they can dial the frequency. They can, the distance between these clumps is basically set by the frequency of the rotation rate. So
Why? So it's a 4m versus 2m and so on.
yeah, something like that. Yeah. So wait, what was that?
No, the mass and so on, the scaling with mass and the frequency, I think maybe.
So I don't know. I'm not sure if I understood what you said, but I just want to make the difference. This is not the rotation frequency.
But this is the frequency of the splitting, no? Of the.
This is just. This comes from. This is a frequency that emerges from just the fundamental constant itself. Okay, there's no external driving.
Okay.
Is what sets the mean angular momentum.
Okay.
That's the experimental parameter under control, right? Once the mass and the equilibrium distance is fixed, you don't change this omega r. I think you're right. It's essentially it's the LZ square over 2I h bar, right? Right.
Yeah.
Just the moment of inertia. Moment
So,
square over twice the moment of inertia times h bar.
Yeah. So this would also hold good for a single ion rotating, right? I mean,
I think
maybe
apart from
apart from the eye.
Yeah. Yeah, that's precisely the question I'm asking.
That's precisely what he's asking, probably. Yeah.
So you're asking why 2 were used instead of 1?
Yeah, and there I think the omega r will scale differently, whether you have two ionic molecule or whether you have a single ion.
Yeah, I think the way to think about it, if I can interject for a moment, Sri, I mean, the two ions there, now once they're locked and you're rotating them, I mean, essentially this is like a rotating diatomic molecule.
Yeah.
And the energy expression written there is precisely the usual L squared you see when it is rigid rotation. And the D term is basically what is called as the vibration rotational causes centrifugal distortion.
That's exactly it. That's exactly it.
That D is the centrifugal distortion. So essentially, if you think about a rotating diatomic molecule, I mean, the spectra that you're seeing and things like that, I mean, this is entire in the oscillation. So this is, so you can translate it to that, essentially.
Yeah. So I think, Saikat, let me answer that. So I think I know why they use 2. They need a Coulomb repulsion to set the equilibrium radius or diameter.
Okay, I see. Otherwise it will fly off.
Yes, exactly. Or go into the center of the trap.
Center of the trap, yeah.
Right? If there's just one ion.
Okay.
Right. So I'm hoping actually you guys can get interested enough in this to have some more insight, because I thought it
but you can always have a Mexican hat kind of a potential, no? So which will give you a single one going around. So I mean, Coulomb repulsion need not be the only one that keeps it apart, no? No, I'm just kidding. It's just
No, the rotation,
really-
the rotation actually gives, so in the molecular context, when you have high rotations, basically it creates what is called as a centrifugal barrier.
correct.
Okay,
So that itself would be enough.
So
Yeah.
the two ions and they're vibrating, and if they're charged, if you don't do anything, they're just going to fly apart. So basically what is happening, that higher the angular momentum, the higher the barrier is. So
Correct.
basically stabilizing that. And now you are exploiting that to sort of now separate out those components.
No, no, I'm saying is one can go into the reduced mass picture, right? Which would be a single mass going around the center, right? The origin. So won't it have similar features? Is what I'm asking.
I think if you could create a potential for a single ion and set it into rotation in exactly the same fashion, I think the features would be similar. What do you think, Saket?
No, I doubt if the single ion will do it. I mean, my 2 pence, without I'm not an expert in this, I'm hearing to this for the first time. You need the two ions because basically it is simulating a diatomic molecule.
Oh, I understand what you're saying. I think the second term will not be there for the
second term will not be there. Yeah. So,
correct. Absolutely. Okay, so that was already nice. Now I am going to switch to what our collaborators are doing and what we are doing. So here the idea is very nice. You know, it's a specialized trap. It's got nice circular symmetry. It's you know, they've shown proof of principle coherent control with two ions. Very nice. What I want to sort of emphasize is that, and this is not our idea, this is the funny thing that our experimentalist collaborators were seeing, is that using just the workhorse, which is present in every lab, you know, every lab may not have that nice circular trap, although I'm sure they could make it. It turns out that even in the linear Paul trap, there are some very interesting rotational configurations that can, there's a variety of them that can be interesting for some applications. So I'm not going to talk about that. So this is the setup in Garching. They also have the linear Paul trap. You see the end caps here. Then you have the 4 electrodes, 2 of them with DC, 2 of them with the RF. And then I would point out that they use an extra metal plate for fine tuning. So they call it the compensator. And in the model, this leads to some asymmetry because otherwise the system has got reasonable 4-fold symmetry around the axis here. So if I try to represent schematically, if you put 2 ions and the end cap voltages are not very high, then they will localize themselves along the axis that joins the end caps, which in our case is the Z axis. Okay. And then I've lined up the Y with the DC and the X with the RF. Actually, I have not done it, Arpita has done it. What they found is that in cooling, okay, sorry, before that I have to say. So if you now increase the end cap voltages, the 2 ion crystal will crumple and the 2 ions will come into the XY plane instead of being on the Z axis, okay, in the XY plane. And they found this was happening, and because they were shining laser beam on it to cool it, somehow the laser beam was not perfectly aligned, so it was a little bit misaligned from the center of the orbit. They found that this rotated the 2 ion crystal. Okay, so I just want to emphasize that this is rotation not caused by any external voltages. It's not caused by the orbital angular momentum or polarization of the laser. It's actually caused by the linear momentum of the laser. Okay, because there's a lot of work in those other areas. Actually, these ion rotation, the rotation of these ion crystals was observed a long time ago by Dave Wineland and his collaborators. They didn't characterize them. They said, okay, we see these crystals and some of them appear to spin. It's kind of cool. They didn't really put any electromagnetic fields or laser light into their model. Their model basically had the Coulomb repulsion and the trap energy, and they were able to reproduce the crystal. So here I've sort of cut and pasted you can tell how dated the paper is by the quality of the images. So this was the case of 2 ions. This is their theory. This is their experiment. They kind of see the 2 ions rotate. Here is the zigzag that I was showing you. Our collaborators have also seen it here. Here we get some more interesting types of rotation. So now you have 3 of them rotating in a loop and the other 2 vibrating in a static fashion. Here's one single one vibrating inside a loop. Here's a chain, the smallest chain you can think of inside a loop. Now here's a loop inside a loop, but they're planar. And now there is a non-planar arrangement. Okay, so there's a whole zoo of rotation animals already contained in the linear Paul trap, which kind of we thought was interesting and worth exploring. Actually, these configurations were first predicted by Lord Kelvin for Thomson's plum pudding model of the atom. In the plum pudding model, you'll remember the nuclear charge, which is positive, occupies a finite volume, and the electrons are embedded inside that positively charged sphere. And if you do some elementary electrostatics, you can figure out that for small displacements, each electron basically sees a harmonic restraining force. And that's essentially what the ions see inside the trap. So it's not surprising that you kind of see similar shapes. So my point of this talk is that we have found that the linear Paul trap allows for elliptical orbits, for multi-loop orbits, which will give you insights into maybe rotor-rotor interactions and interactions with single or chain like vibrating ions. So, you know, if you want to do like the Haffner group at Berkeley has done, work with a single loop, then you can manufacture superpositions, because you can put the system into a linear combination of various rotor states like they did to show the Rabi and Ramsey. But if you want entanglement, for example, you need another rotor, right? If you want states which cannot be written as product states, then you need 2 rotors. And this sort of is a natural candidate for that, maybe. But the classical mechanics of all this needs to be worked out. And so that's our first step. Okay.
Okay, can I ask a very quick question?
Yes, please.
Yeah, do you also see kind of knotted topologies in this?
No. I mean, we have this. Arpita, how many ions are in this last one? 15?
I think in this, I think about 16. The
16.
last one. Yes.
You have gone up in your simulations. You have gone up to 20.
Yeah, I have.
Yeah, so we don't see that yet, but you know, with a sufficiently large number of ions and a sufficiently powerful computer, I think it might be.
Mishkat, I had a comment. If
Yes,
that
please.
so, there must be a Bessel here as well.
There must be a Bessel here as well.
After all, there's circular symmetry, so there must be. No.
So we are sort of. This laser is shining in the. Can you see my cursor?
Yeah. No, I understand the laser and the origin of the rotation, but the fact that the pathways are circular, there must be a Bessel, no?
Probably.
No, is it? Okay.
No, I don't know. Actually, we have not looked at the quantum version of the problem at all. That matrix element was for the quantum treatment of rotation, right?
Correct. No, what I'm saying is with rotation, Bessel should come in.
It should.
So if it does, and then, you know, if particularly these double chains that you have, 2 rotors, you know, one could switch off one of them by just choosing a 0 of the Bessel.
Yes, and there is another way also. I'll show you.
So
I'll show you. Yeah. One thing you have to remember, Harsha, and you're probably getting it, but I just want to clarify for everybody. This laser beam propagation vector is actually in the plane of the circle. It's not perpendicular to the circle.
Correct. And it is misaligned a little, right?
And it's misaligned a little.
So it's an intensity dependent radiation pressure.
I will describe that in detail. It's the scattering force. Yes.
Yeah. Please go ahead. Yeah. Sorry.
Okay, thank you. No problem. That's a great question. Okay. So I told you that the ions are in a harmonic potential, and that's true. But there is also this micromotion, and there is a way of averaging over that micromotion to sort of give you the effective potential, the effective potential that the ions see, and that's called the pseudopotential. And if you calculate the pseudopotential, you will find actually that, well, if you just do the trap, the Coulomb repulsion, you will find a circular trap, which is completely symmetric, and there is no preferred position anywhere. But the 4 electrodes and the pseudopotential they create basically leads to 4 minima along that circle. So the trap is no longer homogeneous, it's no longer rotationally symmetric, it sort of has 4-fold symmetry. And when you crumple the 2-ion crystal, depending on the conditions, it may choose itself along one or the other diagonal of this image. And to further complicate matters, remember that compensating electrode I told you about? How much voltage is put on that? The number of potential minima may change. They may change alignment. So you might have just 2 left, but vertical, or 2 left, horizontal. It depends on the amount of asymmetry in the lab. So we have not worried too much about this. We're still working with the experimentalists to sort of figure out what is the realistic thing to do. But what this leads to is just simply a different initial condition. Okay, so if this is if the second plate is the one that's relevant, then we'll just have an ion crystal that starts this way. But what we're really interested in is what happens when you shine light on it. So now we are shining a slightly off-center laser beam on this configuration, and we are varying the power in time so it hits a maximum and this is just a Gaussian variation. Okay, so this panel shows what we see. At first, the 2 ions are simply vibrating with very small amplitude at the locations of the pseudopotential minima. Then if you crank up the power, they start oscillating with larger amplitudes, reaching almost around the whole circle and inevitably, finally executing full rotation. If you keep raising the power, actually the rotation stops, goes back to vibration, and at the highest power, completely quenches. Okay, so now I explain how this happens. It's reasonably straightforward, I think, but still interesting. So a couple of things I want to sort of point out before I do that is that, as I told you, the trap torque which the ions experience is periodic. That's this blue line here. And if you think about it, the optical torque is also periodic, it's non-uniform. So remember, this laser its original function was actually to Doppler cool these atoms, which means it's very close to resonance. It's only half a line width, red detuned to the transition. And so that's below the transition energy. And so it's pretty close to resonance. So the gradient force is actually very small. Most of the force is a scattering force. And if the crystal is lined up along the laser wave vector, you can convince yourself that the torque is 0. And if it's lined up perpendicular, then the torque is maximum. So it must be varying. This is just sort of a hand-waving argument, but if you plot it, this is what it looks like. And of course, it depends on exactly how much the laser is off-center and what's the alignment and what the angles are and so on. It's sensitive to that, but that basically varies along the. Okay. So this is Arpita's plot of the various coordinates of the ion crystal. This black line, which goes up and then comes down, is the Z coordinate, which basically shows the radiation pressure for pushing of this optical beam. And then the blue is the X coordinate and the red is the Y coordinate. Those are the 2 coordinates in the plane of the circle. Okay. So here I think she has shown X and Y. So you can see that the motion is not uniformly circular. Otherwise, these would have been sine and cosine curves. What is happening actually is that there is a portion of the trajectory along which the ions move slowly, and then suddenly they zip through and slow down again. Okay, so this is sort of the stick-slip kind of motion. So if you had an image, even averaged over time, of the system, you would, if you plotted density versus position, you would see the ions spend most of their time at certain places and quickly pass through the other places. So here you see the data, the pixelated points, where the ions basically spend most of their time at these two diametrically opposite positions, which are brighter, and then zip through these relatively darker places. And actually the theory is right on top of the experiment, but it's a zero temperature theory, so the line is thin. The real temperature is something like 3 millikelvin. But the Duke and Arpita were able to basically match without any free parameters the locations of these ion position maxima with experiment. Okay. So what's happening here is basically that the laser has to become sufficiently intense to free the ions from the trap minima, right? As the optical torque grows, it overcomes the trap and the ions start to vibrate with larger amplitudes. And when it completely overcomes the trap, then not free, but complete rotation occurs, okay? And then the combination of these two torques designates where the ions will move slowly and where they will move quickly, okay? Basically, they move quickly where they see the least resistance. So that's the 2-ion case, and this is actually the 3-ion case, both theory and experiment. So the theory now I think includes temperature, I'm not sure, but there are 3 points at which the 3-ion crystal moves slowly, and then these are the blue or the black for the data are the positions where these ions are basically moving through very quickly. Okay, so this is like a ratchet or a gear of some sort, or you can think of it in terms of these nanofriction experiments where the crystal gets stuck and then moves and stuck and moves and so on and so forth. Okay, so this is not homogeneous, uniform circular motion like in the case of Haffner's group, but we are able to change, for example, the ellipticity of this. So you see this is more elliptical than circular. And then I'll mention briefly an application for just this kind of velocity profile. So let me discuss that. So here we show the power again. And this is the angular momentum of the 2-ion crystal. So you can see that for some time, the power is not enough to create any angular momentum. Then you see a small event here. So this, in the language of nanofriction, is called a precursor event, where you have one slip and then nothing happens until you get into a more regular regime where the ions are now going like a ratchet. So they're moving all the time, more or less, from this baseline orbital angular momentum you can see, but then there are these peaks where they zip between in the dark regions. Okay, so one of the things you can immediately notice is that when the power hits the maximum, actually that's when the angular momentum hits the minimum in its rotational state. Okay, so if we had made this large enough, actually the rotation would have come to a stop, and I'll explain that in a second, but I sort of want to go through this first. So this is just the power of the laser changing. We can also change the offset of the laser, basically where the place on the coordinate scale where it shines from, and also the angle. And you can look at these angular momentum plots in both cases. If you change the offset, it kind of looks symmetric when the power is going up and power is going down. If you change the angle, you see maybe some hysteresis. Okay, this piece is not exactly the same as this piece. And the reason we're interested in that is because it gives some indication of the nonlinearity of the system. People have seen this kind of hysteresis if the number of ions is very, very much larger, like 10 to the 7 or so, sort of like a plasma, but rotated optically. Wineland did some experiments on this. I should have put the reference here, but apologize for that. But that's kind of an examination of what this, what cycling the power basically does to the rotation in the system. But now let me tell you about why things come to a stop if the power is high. It's very simple. So the beam is pushing both ions Because the Coulomb repulsion is stronger than the optical scattering force, I can basically assume that these two ions will always be diametrically opposite each other. They never come close and sit next to each other. The Coulomb repulsion is too strong for that. So that means I can think about this essentially as a rigid rod. There's just a dumbbell rotating about its center. So that means if I have an off-center Gaussian beam, the scattering force on this atom will tend to rotate the crystal clockwise, and on this ion tends to rotate the crystal anti-clockwise. So if the difference between these two is very small, too small to overcome the trap potential, the pseudo potential, then the crystal will stop rotating. So that happens in two cases. First, if the two forces are already very weak, so if you have low power, then the difference between these two is just not enough to make the crystal rotate. So that's this sort of regime here in the graph. But on the other hand, when you make the power very high, the scattering force actually saturates. And now the difference between having 160 microwatts and 170 microwatts is not large enough to supply the torque to overcome the pseudo-potential minima. So that's why when you raise the power, the angular momentum goes down. If you raise it sufficiently, it comes to a trough. So if you could use a small pulse, which is very short, you could swap the positions of these two ions. Or waiting for the ion to slow down, you can actually bring it to a halt by just adjusting the power on your laser. Okay, so I hope that explanation was clear enough. Here's a list of parameters. Maybe I can point out that the experimentalists work with beryllium. Transition wavelength is about, it's in the ultraviolet. Line width for the cooling transition is about 20 megahertz. What else do I? Laser was focused down to about 70 microns. Temperature is about 3 millikelvin. Yeah, the laser angles. I don't know if these are sort of the parameters they gave us and the fundamental constants, and Arpita and Duke were able to fit basically those images I showed you with those parameters. So here's a more comprehensive gallery of their work. So this is the 2-ion case. This is the 3-ion case. I don't think we had data for 4 ions. We had the 5-ion case, which also theory and experiment match very well, as well as 6, nothing for 7 or 8. We had something for 9. And now if you, so this is, I believe, both theory and experiment, but if you use the right parameters, you can get both the inner chain and the outer loop to rotate at the same time, okay? If you go to the case of 11 ions, this is more explicit. Here you can, by suitably moving your laser, keep the inner loop in place. So this is not rotating, just the outer loop is rotating, or have rotation for both, okay? Same thing with 13 ions, but now this is actually non-planar because there are 2 loops on the inside. If you look from the side, you'll see there are these 2 loops, okay? So we're just trying to, we're getting a feel for the dynamics of these systems and see if we understand their classical mechanics before thinking about anything quantum. Okay. I just want to say a little bit about why this is useful, although it is not uniform circular motion. So there's a very interesting proposal from the group of Serac, actually next door in the same building probably, where they talk about analog gravity. I don't know much about this, but here's what I do know. So they have a ring of ions which is moving, which is rotating, and the rotation is not uniform. As you can expect, in addition to this rotation, the ions are interacting with each other via Coulomb repulsion, and that leads to phonons in this crystal. And these phonons propagate with a certain velocity. Now, if there are 2 ions which are separating with a velocity faster than the phonon propagation velocity, then the phonon cannot propagate into that to that ion from this ion. Okay, so this is the so-called supersonic region, where you have sorry, so where it cannot get out of is the supersonic region, and the neighboring region is the subsonic region, right? So the idea of a black hole is that nothing escapes from it, and that's if the phonon cannot escape, then it's confined within the black hole. So here's their schematic. This doesn't always happen. There are certain regions where the ion velocity becomes larger than the phonon velocity. That's where you have the black hole. Now, in Hawking's conception, I believe, if two particles are created at the boundary of a supersonic and subsonic region, and one propagates into the black hole, basically cannot leave, and the other one is typically the one you, in principle, would get to observe. Actually, if you could measure correlations between those two particles, they are entangled. They're in a two-mode squeeze state. So in this realization, you can actually reach inside the black hole and do momentum correlations with the particles that are outside and inside, and that's exactly what you see here. This is the correlation function plotting. So this is supposed to be a signature of Hawking radiation, as I understand it. So for this to work, the velocity profile has to be stationary but inhomogeneous. So I interpret that to mean stationary means it stays the same over time, meaning it repeats itself, and inhomogeneous means it's not the same everywhere on the circle. That's exactly what we have here. Okay. If the power of this pulse was constant, you would just see a comb of peaks. So it's stationary, but it's not homogeneous. So of course, this proposal was for a larger number of ions, I think about 1,000, maybe 100 in a follow paper. But it would be interesting to see how the dynamics of this works in our system and how close we can come to seeing some signatures of this kind of analog gravity. So finally, a taste of the theory. So we used a semi-classical model. Basically, the motion of the ions is classical, but the internal structure is quantum mechanical. And that basically accounts for light-matter interaction, but the light fields are also not quantized, they're classical. So here you have a term that corresponds, that arises because of the motion of the ions, it's the inertial term. This is due to the collision with background gas. These are due to the DC and AC trap voltages. This is Coulomb repulsion force. This is the optical scattering force, which has in its detuning term some velocity dependence, which basically gives us Doppler cooling. And at high intensities, basically saturates to some number, which is the same for both ions. And then you have fluctuating thermal force, which is responsible for representing the temperature, finite non-zero temperature of the system. Okay, so I've shown you a lot of numerical simulations, but I have to, I'd like to share some results that Duke came up with, which are extremely useful and insightful using very impressive analytics. And so he figured out that when the ions were sitting at the minima of the pseudopotential, you could write their axial, radial, and azimuthal frequencies analytically. He derived conditions for ion crystal rotation, which have to do with trap stability, and laser offset and alignment, which were extremely useful in finding the right places for the numerical simulations to start. He figured out the diameter of the orbit. I think this fits to about 80–85% accuracy. The angular frequency of rotation, I think I'm missing an omega/2 here, which is the RF. In terms of the optical force, the damping, and all the laser offset and alignment parameters, the size of the spikes of the angular momentum you saw, I mean, I could have never done that, I'm sure. So this was extreme. This is just a few of the results. I'm giving you a taste. But he has a pretty extensive theory worked out using the analytics. It's very useful. So to summarize, we've considered two ion optical rotation. We found circular orbits. We found this actuation, rotation, and then quenching sort of as a function of power. We found a stationary but inhomogeneous velocity profile. You can think of in terms of nanofriction. You can think in terms of maybe some analog gravity. And then we saw some hysteresis. So This is a little bit old slide. We've already gone beyond. Arpita has told you she's looked at 20 ions, and we're looking at some of the other things right now. So thank you very much for your attention. Hopefully that was a useful use of your time.
Thank you, Mishkat. That was fantastic. So I think, well, if there are questions, just unmute yourself and. Well,
yeah, hi Mishkat.
Sekat.
Sekat, yeah. So, so in this system, the systems are basically highly nonlinear also, right? Like because of the Coulomb sitting there.
Yeah,
right.
Definitely.
So in some ways, this initial potentials, I can think of these as fixed points versus limit cycle kind of dynamics.
So what exactly do you mean?
As in, like, I'm saying that if I do not think of the ions crossing and so on, and if I just look at the equations that you presented, then they look like kind of this, cubic and higher order nonlinear terms in R.
Yes.
So then I would expect, like, I can think of this then in this phase space where I'll search for fixed points. I'll have limit cycles, which basically will actually mean you kind of more uniform circular motion, maybe, or maybe it might have loops and so on. And then there might be chaotic regimes also, right?
So we sometimes saw what we thought was chaos, but Arpita, correct me if I'm wrong, we never confirmed it, right?
Yes, that was not actually chaos. So I think that was coming from some numerical artifact. Or...
But do you see bifurcations or like period doubling and so on? Like those
I don't. Arpita?
I can't, Shweta, I cannot say much about that. So actually, numerical simulation that has some approximations. So maybe we can look at that.
Okay.
Yeah.
Very nice work, Vic. Extremely interesting.
Thank you, Zekat.
Okay, other questions?
Yeah, Srihari,
Yes,
just two quick questions. So one is, in all this work that you had, you didn't really, I mean, the theory doesn't really involve the vibrations coupling into the rotations of the ions, right? Yet, or simply the rotation and just a pseudo potential coming from this?
So that's a very interesting question. I should have put it in the list of future work. So actually, in Wineland's paper, I don't know if you can still see my slide. In his conference proceedings, he has actually done the spectroscopy of the 2-ion vibrational. Can you see my slide?
Yeah.
So in the Coulomb clusters of ion and a Paul trap, he has actually the spectroscopy of the vibrational modes of the 2-ion crystal, but he's not concerned with rotation. So I think he's looking at a static,
right.
Where these modes are actually. So one of the things we've been discussing with our experimental collaborators is that what happens to that spectrum when the ion crystal starts rotating, and so do you see these rho vibrational interactions? So that's exactly, you're absolutely right. That would be interesting to look at.
Right. Okay. So the second thing sort of links back to what Saikat was asking. So in that theory slide, you had finally that one monstrous slide of that equations with the dissipation and all the kitchen sink forces that are acting on the thing, right?
Yes.
So I mean, if I sort of remove it, I mean, in the sense I see this as a sort of a Matthew equation which is damped Matthew equation with inhomogeneous forces coming from all over. I mean, so I was thinking if Saikat's sort of thing is right, this is already a nonlinear system. It's basically damped pendula, x and y direction. But then you have all these the inhomogeneous forces there, so it's going to be. I mean, there might be some interesting phase-space structures.
Oh, absolutely.
But it's sort of one has to figure out exactly. I mean, that force part on the right-hand side there's lots of stuff sitting there. So
there's lots of stuff there. Exactly. Absolutely. I agree.
Yeah. Okay. Thank you.
Yeah. Thank you.
Other questions? There is one in the chat box. This is from Shenu. Maybe I can just read. Nice talk. You are studying rotations induced by momentum of light. What is the purpose? What about the rotation induced by OM of light? That has any consequence?
Right. So like I said in the beginning, there is a lot of work on what the OM does to an ion placed in, let's say, a regular Gaussian beam. I think there is also now some experiments from Schmidt-Kahler's group in Germany. So in that case, the physical mechanism is different. The orbital angular momentum is different. Actually, I think Babiker also has a paper on rotating ions with orbital angular momentum of light. It's a theory paper, long time ago, PRA. If the trap is homogeneous, then the circulation is uniform, I suspect, given some damping and so on and so forth. So this is, our work is, like I said, slightly different. It's based on linear momentum transferred by light. So if you look at the way the laser is coming in here, it's basically pushing these ions. I think I had another slide here which showed that. And so what's interesting about this force is that as the ion crystal rotates, this force is modulated, right? The torque is modulated. So you see the scattering torque changes. And that leads to this non-uniform motion, which is interesting from the point of view of nanofriction and maybe simulation of black holes. That's the difference.
Okay. All right. Any other question?
Yeah, Mishkat, Harsha here.
Yes, sir.
Yeah. So actually, lovely talk. Enjoyed it. I just wanted to tell you, I think if you either keep the force constant for a longer time at some sweet point, you might get the structure which Saikat is talking about, because few cycles is not enough to establish chaos and so on. The other thing you could try out is certainly amplitude modulation of that laser. So that will have its own period, and there'll be other periods which are, then you can see this period doubling. I think there is hell a lot which is going on, and I think it's an amazing piece of work.
Thanks.
Particularly, I like that ugly slide which Shihari says, lovely analytical results. I love that. Very nice.
Yeah, Duke has
please,
done a fantastic job.
Yeah, please share that little detail with us in terms if it's written up. So that will be nice. Yeah.
Sure. Thank you. Thanks so much for coming.
Yeah, I would like to just interject just to make sure that I didn't use the word ugly for sure. Okay, I just said. I myself being a theoretician, I have no form of seeing very ugly equations.
No, but Srihari, after lockdown, kitchen sink means ugly to us.
Yeah, no, maybe I can sort of ask sort of the one final thing which is on my mind. See, what is interesting about these ions, and I mean these sort of collection of ions and sort of engineering them to sort of make different structures, is that you're making these sort of artificial molecules now instead of artificial atoms. Some time ago when a lot of people thought that molecules could be used to sort of as generate qubits and do lots of interesting things with them, molecules themselves. Mm-hmm. There are limitations there. So I mean, obviously, people realize that you can't really scale them up so easy. The issue. So what I was going to ask you was, so making these artificial molecules now, of course, you have greater control over how you're going to modulate these couplings and make them. So is this now when one expects that this will sort of overcome some of these limitations that the molecular systems were facing, or?
Good question.
I mean, could one actually engineer these so that it overcomes these sort of molecular, there are some coupling constants in molecules which is given by God, and there's nothing you can do about it, that's that.
True.
But here you can engineer these.
True. Yeah. So absolutely, that's an interesting question and sort of a very nice perspective on. So actually, I go back to my graduate school days when I was trying to make. I used to be an experimentalist, and I was trying to make cold molecules from cold atoms, and these proposals were very talked about and cited about using molecules for quantum computation. So one thing, we're sort of in I'm not very sure about scalability issues here, but we are sort of in the few ion regime, which still gives us enough room, for example, in this picture to look at how maybe these artificial molecules talk to each other when they're rotating. If we can come up, instead of this 15 ion 45 equation description, if we can come up with some sort of effective loop variables, which I'm starting to sound like a quantum gravity person now, which interact with each other and sort of reveal to us if there's a simple way to think about how to engineer these parameters, so we can transfer quantum information coherently and so on. So yeah, definitely very interesting.
Okay, thanks.
Excellent. All right, so I think we can. Second, you have more question?
Yeah, I had just a quick question. Since earlier in that 2017 work you mentioned about coherence, and here also, since you have this very well-defined rho vibrational state, the question is, for example, with a Raman beam, can you induce coherence and measure its or store a photon in it and so on? Like
exactly. Absolutely. Yeah.
All right. Okay, so well, if there are no further questions, maybe we should thank. We can't clap. Well, we can clap a little bit, but I don't, since everybody's muted, we can't hear. But let's
thank you.
Thank Mishkat again and again. Thank him for giving this fantastic